Okay, so the last part of this lecture, we're going to talk about rare earth elements, which are a very special group of trace elements, really, really useful. And then, as I mentioned, we'll end talking about large igneous provinces. So we'll start with rare earth element patterns. And even before that, what are rare earths? So the rare earth elements are this, REES, that's actually what people call them. So REES, and I'll probably use the abbreviation a lot because otherwise it's a lot to spell out, but when I'm speaking I'll usually say rare earths. So there are these elements along the bottom of the periodic table in the big red box there. You might also see them called the lanthanides because the first one is lanthanum. And these are probably a bunch of elements that you won't encounter much in your day-to-day life. If anyone's heard of dysprosium before, nice one. But these are quite useful in technology. They're used in phone screens. They're used, neodymium makes the magnets that are used in wind turbines and all kinds of stuff like that. So they're becoming increasingly important. But geochemists were there before it was cool, and we've been using these for a while. So yeah. The really cool thing about rare earths is that essentially every rare earth element normally has a 3+ charge. And this is quite unusual. And because we have this increase in atomic number across, we have a very, very systematic change in behavior. So we always have a 3+ charge, and the exceptions are europium, which is one of the kind of middle rare earths. It's in the middle of that sequence. That can be a 2+ charge in reducing conditions. This is the same as saying it's less oxidized, and like there's less oxygen around. And that, as a 2+ ion, europium is compatible in plagioclase, and that will be important later. Cerium, which is one of the light rare earths, it's towards the left of that group on the periodic table, can be 4+ in very oxidizing conditions. There's also a systematic variation in ionic radius. And the light rare earths have large ions and the heavier earths have smaller ions. Now, I know that's slightly different to what I was talking about before. I said that, as the atomic number goes up, the ion tends to get bigger, but that's in very broad terms from like hydrogen to uranium. Across a group like this, there is actually this systematic change towards smaller ions, and I can't quite remember why that is. No worries. So this plot here is showing the coordination number of the different ions, and here is the ionic radius. So on the left, if we have a small coordination number, so this is 6, so this will be an octahedral site in a mineral, then the ionic radii start at just over 1 for lanthanum, and they go progressively down, and the heaviest one here is lutetium, and that's about 0.85. Often we'll be dealing with these coordination number 8, and the lanthanum's about 1.1, lutetium's about 0.9 something. Yeah?
Was the y-axis the size, or would you say ion size?
Yeah, ionic radius, so radius, that's the size basically. There's also a couple of others that are thrown in here. These are just, indium and scandium. These are also elements that are commonly 3+, but they're not rare earth elements. All right. So here, because they all have 3+ charges, then we can really separate just the effect of the ionic size on the partition coefficient. And this is something called an Onuma diagram, and it's just a plot of the partition coefficient on the y-axis, and this is a log scale, right? So we've got huge changes in partition coefficient against the ionic radius. And what's quite cool with these diagrams is if you plot it up, you can actually see where the ideal size is for this particular site. So this is an olivine melt partition coefficient for all the rare earths, and you can see that the ideal size is for a 3+ charged ion in olivine, in I think either the M1 or M2 site, because they're very similar, is about, you could read that off as maybe 0.72, 0.74, something like that. And you can see that there's a very smooth relationship between the ionic size and the partition coefficient. It starts to get a bit wonky down the bottom, and this is probably just because the concentrations of cerium and lanthanum in olivine are so low, they're actually really, really hard to measure. So here we have the heavy rare earths on this end, so this is ytterbium, this is the second heaviest rare earth, and that has a smaller ionic radius than the light rare earths, and it's still incompatible in olivine, but it's less incompatible. It's slightly more compatible in olivine, although it still doesn't fit very well. Lanthanum and cerium, which are the light rare earths, they don't fit at all. They have very, very low partition coefficients, 10 to the minus 4, so that's 0.0001. And this is the case for lots of different minerals, and the rare earth elements are pretty much always incompatible in mafic minerals that are crystallizing from melts. But again, the light rare earths are generally more incompatible than the heavy rare earths, and this is really useful. There's also this other thing to note, is that the heavy rare earths are compatible in garnet, and we'll come back to that later. So if we want to compare the concentrations of rare earth elements, there's actually a couple of things that we need to think about. The first thing is that different elements have different abundances in the solar system. Should be fairly obvious. If the sun is mostly hydrogen, and the sun is like 99% of the mass of the solar system, so we've got loads of hydrogen and a lot of helium, and then kind of a general decrease in the amounts of these different elements in the solar system as a whole. So the building blocks of Earth would not, we wouldn't have the same amount of every element. It should be fairly straightforward. But there's this effect called the Oddo-Harkins effect, and this is to do with how elements are made in stars, in supernovas, and during the Big Bang even, that we have a preference for even-numbered elements. So if we compare, say, iron here to, I actually can't tell what that is, titanium here, which has an even atomic number, to vanadium, there's more titanium in Earth and in the solar system in general. So if we just plot raw rare earth element concentrations, we have this like zigzag effect where we're basically going odd number, even number, odd number, even number, odd number, and so on. And it's kind of useless for comparing stuff because we just see the spikes. It's not very useful. So we want a way to smooth this out so we can compare concentrations of different rare earth elements in a meaningful way. And these, it doesn't massively matter what they are, but this is seawater and then a bunch of geological samples, sediments and basalt. Yeah?
So the preference is just that if it has an even number, it has higher concentration?
Yes. It has higher concentration in the solar system and in the Earth as a whole. Okay. Yeah. So this is absolute concentration. Absolutely. Yeah. And so what we do is we normalize the data. And so typically you'll divide it all by one of two things. The first one is something called CI chondrite. And CI chondrite it doesn't matter what it is, it's a type of meteorite. And it's a very unique meteorite because it basically has the same abundances of different elements as the solar nebula did. So it's very, very useful because we can pick up these meteorites and we can go measure them and get a really, really precise measurement of what the original solar nebula was like. I think that is, this is actually the CI chondrite composition. So if we imagine we measure the spiky pattern in our rocks here, and we divide it by the spiky pattern here, and basically the spikes cancel out. The other thing that we can normalize these two is something called PUM, or primitive upper mantle. You won't always see this for rare earth element patterns, but you will see it for trace element patterns that we'll talk about next week. And so this is a hypothetical mantle composition, which is if you take the overall composition of the Earth and we know how big the core is, we basically remove the core, and then that gives us our primitive upper mantle. So the idea is that this is what the mantle might have been like before any continents formed or any crust formed. In reality, probably never existed because crust was already forming as the Earth was coming together, but it doesn't matter. Either way, whichever one of these you divide to, you get these nice smooth patterns. And so now we can see these really systematic variations that are just coming from the different partition coefficients that these different rare earth elements have. It's not coming from this spikiness in the original concentrations. So I've put two rare earth element plots. You see that they're usually plotted with a log scale, and the y-axis is the concentration in the rock divided by the concentration in Ci chondrite or primitive up mantle. And we always plot the light rare earths on the left and the heavy rare earths on the right. And they're just arranged in order of atomic number. You'll also see a lot of them have this gap at PM. PM is promethium. It is an element that doesn't have any stable isotopes. So it probably existed when the solar system formed, but it's all decayed away. So remembering what we said about the ionic sizes, the light rare earths are generally more incompatible than heavy rare earths. So if we compare this is a mid-ocean ridge basalt, and this is a tholite on the top, we can see that we have fairly flat pattern. We'll talk about what that means in a sec. If we compare that to an alkali basalt, and I think this is from somewhere in Germany, you can see it's got this very, very steep slope. But we get this very smooth pattern, right? We're getting systematic changes in behavior based on that systematic change in ionic size. All right, go ahead.
So rare earth elements are always trace elements since we're using the partition coefficient?
Yeah. There's some very, very rare intrusions where you get weight percents of rare earths, but for almost everything you're ever going to encounter, they are trace elements.
Okay.
And they're typically present in concentrations of 1 to 100 parts per million. There's not a lot of them. They're rare. So, yeah.
But I just don't understand why dividing with the concentrations in a meteor like that will smooth out the pattern.
Because the meteorite is representing the original concentrations in the solar nebula, right? And that spiky concentration in the solar nebula got turned into spiky concentrations in Earth. And then every rock that you make on Earth, if you just measure the raw concentration, it will be there'll be usually more cerium than lanthanum, and then it'll go down. And so we're just cancelling out the initial variability from how the elements were produced in the first place.
Yeah.
All right. So I've got an example here where we start with a chondrite-like mantle. So if we divide the concentration in the sample divided by chondrite, we get a straight line. Now this is not a log scale. Usually we're going to use log scales, but I'll just point that out. Okay. So if we melt this, and we're just going to take 2 of these rare earths just to illustrate it. So if we have, that's wrong, sorry. So we have lanthanum, and this is supposed to say partition coefficient is 0.2 for lanthanum. So lanthanum is more incompatible than all the others. Then if we do 1 divided by 0.2, we get 5. Right? So this is the first increment of melting a mantle that started with chondritic concentrations. Terbium is less incompatible. It's still incompatible, but it's not as extremely incompatible. This one has a partition coefficient of 0.4 in this example. And so we do 1 divided by 0.4, and that should be just a bit higher than 2. Should be somewhere up here. So both are incompatible, both get concentrated in the melt, but because lanthanum is more incompatible, it gets into a higher concentration in the melt. So we have a rare earth element pattern that is sloped from the light rare earths down to the heavy rare earths. In the residual mantle, we have the opposite thing. After a little bit of melting, we've depleted more lanthanum than terbium because it's more incompatible. Everyone still with me? Okay. All right. So rare earth elements that almost always 3+ charged, and they have systematic variations in ionic radius. This means that they also have systematic variations in how compatible they are. Light rare earths are larger ions and more incompatible than heavy rare earths. We usually plot these as chondrite normalized or primitive upper mantle normalized diagrams to smooth out this initial spikiness. And melts are generally enriched in light rare earths divided by heavy rare earths compared to their mantle sources. Residues, so residues of melting, become depleted in light rare earths compared to heavy rare earths. Any questions about that? It's only one more section on trace elements, and then we get to talk about some fun stuff. So, all right. So typically you're not going to go through every, maybe if you're doing research on this stuff, you'll end up having to do these kind of calculations and figure out how much it's melted and all that. But ideally for you guys, you want to be at a point where you can look at a rare earth element pattern and say, I know what that means, without having to go through the maths of it. So we'll start by talking about degree of melting. So we said before that incompatible elements have the highest concentration at the lowest degrees of melting. But the more incompatible they are, the higher that concentration becomes. So this is an example. Again, we've got a mantle composition that is this carbonaceous Ci chondrite. And at 5% melting, we've got a very, very high concentration of lanthanum. And we have a concentration of lutetium. This is the heaviest rare earth. That is still higher than the mantle that we started with, but it's not as increased. But thinking back to our fractional melting or equilibrium melting plots, as the degree of melting increases, we gradually dilute down these very incompatible elements. And so what you can see here is as the degree of melting increases from 5 to 10 to 20 to 40%, the pattern actually gets flatter. Okay? If we melted 100%, it would have the exact same pattern as the Ci chondrite. And this is just showing that plot again. So just for comparison's sake, the light rare earth here could have a partition coefficient of, say, 0.1, and the heavier earth could be, say, 0.5, right? I don't think those are the exact numbers, but it doesn't matter for showing it. So what would happen at the smallest degrees of melting, we have very, very high light rare earths and moderately high heavy rare earths, and so we have a steep slope between the two. And as the degree of melting increases, these actually tend towards the same value. And when we've got 100% melting, it's completely flat. So the flatter the pattern, the higher the degree of melting. Now, Earth's mantle is not chondrite because we made a core, and then there's been 4.5 billion years of melting, making crust, all sorts of crap. So normal mantle is what is usually referred to as depleted upper mantle, and that's because it's slightly depleted, especially in light rare earths, because we formed continental crust that has quite high light rare earths. So if you added these two together, then you get this supposedly, the hypothetical primitive upper mantle. Yeah. So this is what normal mantle looks like. However, we do have subduction, so we actually have a way of adding enriched things back into it. So most of the mantle is depleted, but we might have little patches that are relatively enriched in light rare earths compared to heavy rare earths. So if we go, if we try and put all this together, we can actually understand those two patterns that I showed you before. Yeah.
I don't really get it. If you put the depleted upper mantle and the crust together, right?
Yeah.
Would that make the same as the contract?
No, it'd make this, if you put the crust, the mantle, and the core back together, then you get chondrite.
Okay.
If you put the crust and the depleted upper mantle together, then you get primitive upper mantle. So that's basically the difference between them. Is primitive upper mantle, people have tried to correct for the fact that the core's been removed. So the core doesn't really have rare earths, so the rare earths are actually always higher in primitive upper mantle than they are in the chondrite. But again, for these plots, it doesn't matter too much which one it is. It'll give you a similar looking plot. It's just the absolute concentration will be, sorry, the number on the scale will be different, but the shape will be the same. All right, so I think we got enough to go back and look at these. So if we look at our alkali basalt first, because it's probably a bit simpler, we have really high light rare earth elements, and we have quite high, but not as high, heavy rare earths, so we've got this steep slope. So that's what we might expect to see if there's a low degree of melting, right? And we kind of already got to that earlier in the lecture, talking about the mantle temperatures and everything in Hawaii. Yeah, so we have the most concentration in these compared to the heavier earths when the degree of melting is low. When you have a high degree of melting, you have a flatter pattern. But in these ones, we actually see there's even a bit of a drop-off. It's not completely flat, right? So if we were melting chondrite or primitive mantle, even if we melt 100%, we can never make something that drops from that the light rare earths are lower than these ones in the middle. So what's actually happening here is we're melting this depleted upper mantle source, so we start with less of the light rare earth elements in the first place. And so even though we're increasing the concentration of light rare earths by melting, they're still kind of low. All right. So mid-ocean ridge basalt is relatively high degrees of melting because it's mainly flat, of a depleted mantle source, and that's because the light rare earths are low. And then the alkali basalts, we could either have a low degree of melting, we could also have an enriched mantle source if we'd added some of these light rare earths in through subduction and recycling, or it could be both of these processes. But the key thing here is the low degree of melting. Okay, so rare earth elements are really incompatible in most mafic minerals that are crystallizing. So this is incredibly useful because it basically means that we can easily remove the effects of fractional crystallization. So when you crystallize something, if we look at the extremely incompatible, this is the fractional crystallization diagram again, as we remove minerals through fractional crystallization, we basically just steadily increase the concentration in the melt. And because all of the rare earths are incompatible in most mafic minerals, we're basically just moving this pattern up parallel. So this is an example, it's from the same one that I showed you in the major element one, where we have a komatiite, and if we crystallize it about 50%, we get a basalt. You can see with the basalt, it's just like someone took the blue patterns here and just moved them up, right? So because we're not changing the slope, we can actually separate these effects of differences in mantle melting from differences in crystallization and magma evolution further down the line. So I just want to note a couple of unusual rare earth element behaviors, and I kind of did note these before. The first one is that the heavy rare earth elements are compatible in garnet. And so this is really useful because if we think back to our mantle mineral types, garnet peridotites are deep. So this actually gives us a way of identifying deep melting. And so this example I've shown is from Hawaii. There's a few other trace elements in this pattern, but it's the same idea as the rare earths, and you don't just ignore the other trace elements. So we have our morb, which is this black pattern, and you can see that in the heavy rare earths to middle rare earths, it's pretty flat. And then it kind of goes off the cliff because it's depleted in the most incompatible elements. You compare that to a Hawaiian magma, and here's a Hawaiian tholite, so we know this is also high degrees of melting. In the middle, it's pretty flat. But the heaviest rare earths are quite low compared to the morb. And that's because the Hawaiian one was melting at a deeper average depth because of that thick lithosphere and because we got the plume melting at a greater depth. And so because more of the melt happened when we were in the garnet peridotite field, those heavy rare earths stayed in the garnet and they didn't come out into the melt. So when we see this kind of heavy rare earth depletion, that gives us a clue that there's deep melting happening. The other one is europium 2+ being compatible in plagioclase. And so this is quite handy in that we can actually identify plagioclase that's been removed or added to a rock based on the chemistry. So here's a rare earth element diagram of two different rocks, and you can see one of them has what we call a negative europium anomaly. So this means that if we basically drew a line between the elements either side of it, it's lower. Yeah?
Just on the top one again,
Yeah.
you said something about the depleted of the heavy.
Yep. Right here.
Yeah, and what did that mean? You said
if the middle rare earths are basically the same as the morb, right? It's in this tholite and in the morb, but the heavier rare earths are suddenly lower. So it has low heavier rare earths, and that's because there's garnet in the source.
Okay.
The garnet holds on to the heavier rare earths when you're melting. So coming back to this one, we have a negative europium anomaly in this rock, so it's lost plagioclase. And in these ones, we have a positive europium anomaly, and they've gained plagioclase. And this is actually a rare type of cumulate rock called an anorthosite, which is basically just pure plagioclase. So it's really obvious. But this can be handy. Sometimes we might see a basalt. We might not see any phenocrysts, but we might see a negative europium anomaly, for example. And then we can tell that it did crystallize plagioclase, even if there aren't any plagioclases in the sample. Okay. And the last thing is that we often use ratios to kind of like summarize key things about these plots without plotting them all together. I think you can probably even see it in this one. When you've got a bunch of different rare earth element patterns on the same plot, it starts to get a bit messy, and it can be a little bit confusing. So when we want to plot a lot of data, then we often use ratios of specific rare earth elements to highlight certain features. So for example here, if we do the light rare earths divided by the middle rare earths, so this would be something like lanthanum is a light rare earth over samarium, then that's showing us either the degree of enrichment or depletion. This is how steep the light rare earth element part of the plot is. So here, this is just, doesn't matter what the rock types are, but in this corner you can see that there's very low light rare earths compared to middle rare earths, so this is telling us that the source is highly depleted. This is just like the mid-ocean ridge basalt. It's got low lanthanum compared to the middle rare earth elements. At the other end, we have high light rare earth elements over middle rare earth elements, and this means that we either have a low degree of melting or an enriched source, similar to the alkali basalt. We can also use something like this gadolinium over ytterbium, so this is a middle rare earth element divided by a heavy rare earth element, and we can use that to identify garnet in the source. So that's basically doing the same thing here of showing that the heavy rare earths are low. So when the heavy rare earths are low, this number is high, so everything in this corner had deep melting in the garnet field. All right. So lower degree melts are more enriched in light rare earths, and they have steep rare earth element patterns compared to high degree melts. High degree melts have flatter rare earth element patterns. The slope of a rare earth element pattern can also reflect re-enrichment in the source if the light rare earths are high, or depletion if the light rare earths are low. Fractional crystallization generally just increases the rare earth element concentrations without changing the shape of the pattern very much. The heavy rare earths are compatible in garnets, and if we have low heavy rare earths, then that can tell us that the melting was deep in the garnet prototype field. And europium can form a 2+ ion, and that's compatible in plagian clays. And the last thing, yeah, we can use these ratios just to summarize some of these key points of the diagrams. Any questions on that? Yeah?
During melting,
yeah,
when we have high concentrations of, for example, light, REES, is that because it's incompatible and therefore wants to leave the melting?
It wants to leave the solid. Yeah, exactly right. Yeah. Okay, that was it on trace elements. So yeah, we got 20 minutes to talk about large igneous provinces, which I think are pretty cool. Hope you guys do as well. All right, so I did mention these at the end of last week's lecture. So large igneous provinces, we talked about the fact that there are these huge outpourings of volcanic rock or igneous rocks in general, and often they're erupted very rapidly on a geological timescale. They form when a plume head, this is like the first rising bit of a plume, hits the shallow upper mantle. And I showed you a picture last week that on continents you often get these big stacks of basalt. So these are called flood basalts or continental flood basalts.
Question?
Yeah, go for it.
So they go like different directions, or do they just go one direction, or like the flood?
Yeah, it's a good question. So I think it gets a little complicated because usually especially on the continents, the lithosphere isn't just all the same thickness like beneath the oceans. So sometimes the plume gets deformed and it goes into a weird shape when it arrives. As for where the lavas flow, that's just going to depend on the topography. So, maybe, I'm not sure. On the Faroes, so I think this was all subaerial, so it was on land above the water, but they're just going to flow downhill wherever they are. And I'm not quite sure which, I don't quite know what the flow direction was here. Yeah.
Each bit, would that be its own lava flow?
Yeah. So each one of these. So I don't know how big this cliff is, but it's a pretty big cliff. So a lot of these lava flows will be like 20 meters thick. They can be really massive. Okay. So continental flood basalts have this. It's called like a traps morphology, and I think it comes from the Swedish word for staircase, which is trappa. It's basically the same in Danish, isn't it? Yeah, but the Swedes got to this one first. So yeah, you can see these are pictures of different flood basalts. This one is the same picture as before from the Faroe Islands. This is the Deccan Traps in India. That's the one at 65 million years ago that's sort of maybe associated with a dinosaur extinction. And this is East Greenland. And in every single case, you can see you get this stepped profile, and that's just from the way that these different lava flows erode. But it's quite spectacular. Yeah, so what happens is that the plume, the head of a mantle plume comes up beneath a continent, and then it starts to spread out. Because you have all this hot rising mantle, you can actually kind of like temporarily raise the topography and then actually drive rifting. So you will often see these large igneous provinces happen right before or like right as continents start to rift apart from each other. So I don't think it's universally accepted, but the idea here is that the plume itself arrives, and it's the plume that's driving the initiation of continental rifting. So a couple of examples here. The Iceland plume, which we talked about before, and it made the North Atlantic igneous province, which is basically everything in red and pink here. And the plume arrival actually drove the opening of the North Atlantic. So the early formed flood basalts are in Scotland, in East Greenland, we have some in West Greenland, and then the Atlantic opened and the continued action of the plume built up the Greenland, Iceland, and the Faroe Island Ridge, and then obviously Iceland itself. Another example is the Tristan plume, which I don't have a picture of. That was another one that I mentioned last week, and that was the Parana Etindeca large igneous province, which is the Parana side is in South America, the Etindeca side is in Africa, and that plume and that flood basalt province coincided with the breakup and the opening of the South Atlantic. So that was about 130 million years ago. The Atlantic didn't open all at once. So different sections of it seem to have been, the opening seems to have been triggered by these plumes arriving. So because you have the combination of a hot plume and you're rifting, so similar to a mid-ocean ridge, because we're rifting, the mantle can decompress a lot. So we can have adiabatic decompression to a very shallow level, but we've got a really hot plume as well. So you have the combination of extra volcanism because of the rifting, and we have extra volcanism because of the high temperature. So we get massive, massive volumes of magma. Yeah.
You say that the plumes caused the rifting?
Yeah. So I think I think this has become controversial recently, but it's essentially the plume is hot, and so you are rising up the continent above it and potentially weakening it, and it provides an opportunity for the continent to rift. So yes, so these large igneous provinces are often associated with continental breakup. All right. When we look at continental flood basalts, they're typically quite low in magnesium. You'll find some picrites, which are fairly high in magnesium, but a lot of them are about 6 to 8% MgO, so this would be even less than a morb. And so what that's telling us is that even though we had all this huge amount of melting, they've crystallized a lot before they made it to the surface. And so actually what's happening is if we have a plume head that's melting somewhere in the lithosphere, the melt is coming up in channels, and it's probably getting stuck at a variety of different magma chambers at different places in the crust and crystallizing a bit and moving upwards and crystallizing a bit and moving upwards. And we end up with these flood basalt eruptions of lots and lots and lots of relatively evolved magma. So we're actually, I think in most cases, about 2/3 of the magma stays underground in these intrusions, and about a third makes it to the surface. So it also highlights how much magma we've got going around. So I want to ask you, based on everything we did with the rare earth elements, what should the rare earth elements look like for something that had very high degrees of melting but quite a lot of fractional crystallization? Does anyone want to have a go at that? So if it's high degrees of melting, should the rare earth element pattern be steeply sloped or flat? I think, Jonathan,
I think it should be flat. It does it all.
Yep.
At once.
Should be flat. But if we have a lot of crystallization after that, what's going to happen to it? So it's flat?
Then it increases.
Nope. Not quite. Yeah?
The milk gets sort of uniformly enriched.
Yeah, so it's flat, but then it's going to get enriched, and it's just going to move the pattern upwards without changing the slope of it. So if we look at what they actually look like, again, this is one of these trace element patterns, not a rare earth pattern, but we can treat it the same way. We have morb here, and it's got that, depleted light rare earths, pretty flat in the middle, and heavy rare earths. And there's a few different flood basalts here. Wouldn't worry too much about it. These little crosses are the Deccan traps that we just talked about. And they're a fairly flat pattern. I put in a blue flat line here, and you can see that the pattern is fairly flat, but it's higher than mid-ocean ridge basalt. You could also argue some of these, like this Piranha one, that's from the Piranha flood basalts, they have a bit of a heavier earth element depletion. I don't know if that's enough to say that there was garnet field melting or not. Same here, these are just some other examples, and the pattern's fairly flat. There's a little bit of a tilt towards the light rare earths here. And yeah?
I don't think I quite understood why you would see a depletion of the heavier.
If it melted in the garnet peridotite field. So if it was deep melting, garnet in the source, when you make the melt, the heavier earths stay in the garnet. So the melt has less heavier earths compared to the middle rare earths. Yeah.
What is the spike in the middle?
Yeah, so this is because it's not a rare earth pattern, so that's actually lead.
Okay.
And maybe we'll talk about this next week, but this is probably telling us that there's some crustal contamination going on. And that's probably what's causing these light rare earths to be high. But again, we'll talk about that in a bit more detail next week or the week after, because it's more relevant to subduction zones. But anyway, yeah, the broad idea is that the rare earths are fairly flat, and that they're quite high concentrations though, because we've got all that fractional crystallization. Okay, that was it on the testing rare earths. Yeah, so we can actually see these plumbing systems in some places, and sometimes these magma chambers are exposed by erosion. And there's a really fantastic example in Greenland, and I'm bringing it up because I think we'll revisit it next week. And it's called the Skaregard intrusion. And you can see this is kind of a map of where the actual different rock types are. So the Skaregard is in blue, and it's in East Greenland, so it's covered in glaciers and cut by fjords and stuff. This is a reconstruction of the different crystallization zones in it, and we'll talk more about that next week. But essentially, there's some progressive change in the composition of the cumulates as we go up. And it's what we call a layered intrusion, because if you look at it, this is just a cliff in the Skaregard intrusion. You see all these lines coming across it. These are different layers in the cumulates. So this is probably a magma chamber that similar to what would have been feeding these flood basalt eruptions. If we go back in time and look at old continental large igneous provinces, sometimes we can only see the plumbing system. We can only see the magma chambers. We can only see the dikes. A couple of examples here. This is the Bushveld intrusion in South Africa, and this is pretty incredible. It's about 400 kilometers across, so this is a just giant magma chamber. It's also where about 80% of the world's platinum group elements come from that we use in catalytic converters and for platinum jewelry and stuff. It's almost all from this one intrusion. So yeah, just a massive magma chamber. Another example, this is in northern Canada, and you can see the scale of this here. This is Hudson's Bay, so that's 500 kilometers. This is probably about 2,500 kilometers long. And this is the Mackenzie Dike Swarm. And the idea here is that it's what they call a radial dike swarm, a radiating dike swarm. So all of these dikes are pointing outwards from some central area where a plume could have hit. But this could have represented some of these dikes bringing magma to the surface. But if there was a flood basalt there, it's mostly been eroded away. So we mainly just see the dikes. All right. And the very last thing is what happens if a plume head arrives beneath oceanic lithosphere instead of continental. We generate these things called oceanic plateau. And you can see on the top diagram, this is just some of the outlines of them in the ocean floor. And I put that up there because you can actually go on something like Google Earth or even just Google Maps, put it on the satellite view, and you can search for these things. So this is the Kerguelen Plateau here, which corresponds to this one on the map. And this is enormous, like absolutely enormous. I mean, there's Australia, we're probably getting towards like a similar length to like the north-south like length of Australia. I mean, it's a huge plateau. And what these are is the areas where the oceanic crust is very, very thick because you had old oceanic crust and basically just dumped a ton of lava on top of it. I'm not going to cover this much in the course, but it's quite cool. So, yeah.
Can you see how old it is?
Yeah, I can't remember how old Kerguelen is. It might be like 130-ish million years, 140, something like that. Some of these are quite interesting. So this one, Ontong Java, Manihiki, Hikurangi, these were all originally the same thing, and then they've been rifted apart. But yeah, the idea is that they could potentially jam up subduction zones because you're trying to subduct normal oceanic crust, and then suddenly you got this big fat plateau, and it just won't go down. So yeah, there's a range of different ages. Weirdly, there was this. It seemed to be like a trend in the Cretaceous that the Earth made lots of ocean plateaus, and I'm not sure why. But yeah. This one actually has a couple of islands that pop up. So it's named after Kerguelen, which is an island. So it pops up above the surface, so people can go and do geochronology there. Yeah. Oh, go ahead.
So the oceanic ones, they don't fractionate as much? Or?
Good question. I actually don't know a hell of a lot about oceanic plateau.
Okay.
Yeah.
I was just thinking if it didn't. Okay, I guess we wouldn't really know if they made a lot of magma chambers.
We'd have to drill them basically, or do you can do geophysical surveys, seismic, that kind of thing, to see if you can see layered cumulus or something. I think they must do, because I think some of them have really quite thick crust. I can't quite remember, so I don't want to put a number on it, but normal oceanic crust is like 6 kilometers, and maybe some of these might be like 20, 25-ish. There's like a lot of and some of that would be lavas added on top, and some might be intrusions as well.
Okay.
So yeah. But if you are really bored, you can go on look for oceanic plateau on Google Earth. So. Okay. So on the continents, the arrival of mantle plume heads cause continental flood basalt volcanism, and it can sometimes lead to continental rifting. Continental flood basalts are pretty evolved, low magnesium, and they form after extensive fractional crystallization in this complex plumbing system of dikes and magma chambers. They're sometimes exposed by erosion, and in older large igneous provinces, we sometimes only see the intrusive part. We're missing all the lavas because they've been eroded off. Yep, and if we have a plume arriving beneath the oceans, then we form these oceanic plateaux. Does anyone have any questions about that? Or you're keen to get going? Yeah. All right, there's the reading for this week. Yeah, you can check it in the lecture notes, and there's the lecture summary. So, yeah, you're free to go.